one of our organizer, Narayana, Santhanam. And you talk about data directed used to be
derived.
Now it's data derived.
Oh.
Data derived point-wise convergence. It
Right.
sounds less sexy than your earlier talk title.
So this is joint work with Venkat, Alec, and Wojtek, and I think Venkat and Wojtek are probably somewhere here. There. So hopefully this is a fun topic. Like, it started off as an observation in a different problem that we are looking at, and it sort of acquired a life of its own. So let's begin with an example. It's a simple universal setup. There's a class of models, and we sample IID from some unknown model in the class. Okay? And we are looking at cases where each of the distributions in the model class is over a countably infinite alphabet. Okay? What we want to do is we want to find an upper bound on all percentiles of the distribution. What's a percentile? The half percentile is the median. So the 1 minus delta percentile is just this point where the cumulative distribution function of the where the CDF becomes 1 minus delta. Okay? So essentially, we want to upper bound all the percentiles. So we want to find this, we don't know this red curve, but we want to estimate a green curve, okay, which is, so that the red curve completely dominates the green one. Okay? So that way we have a finite upper bound on all percentiles if f hat is also a cumulative distribution of this one. Okay? So essentially, this is the task. We have an unknown distribution. We want to find an upper bound on all percentiles. Okay? So very simple. When is it good? Well, if we do find a curve, green curve that is dominated by the true CDF, then everything is good. We say the loss is 0. If not, if anything else happens, right? So the loss is 1. Okay? So we want to somehow simultaneously bound all percentiles. We don't care about what happens at infinity. We don't care when this green curve hits 1. Okay? It can go to 1 at infinity. That we don't care. Okay? So this is the task. And we ask, okay, we keep drawing samples, and hopefully our estimates keep getting refined. And we want to ask, like, what is happening, right? So what are the asymptotics? Well, but yeah.
You don't care about how tight the bound is. You only care about bound.
Right now, we just care about. We don't care about how tight.
Isn't it easy? You just push the curve way to the right.
Well, you want f hat to also be a CDF, and way to the right, you can't push it to infinity because you want finite upper bounds on all percentiles. Right? So you can try pushing it as far. You can make it rise as slow as you want. Right? But the question is, can you do even that? Okay? Because remember, the idea is to look at classes where potentially even this is going to be difficult. Right? So you can make it rise very, 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 very slow, but it has to, for any threshold, if I give you any threshold, like 1/2, it has to hit 1/2 at a finite time. Right? So the whole thing is between whether it's finite or not finite right now. Okay? So you can't say, okay, this is going so slow it is 0 and it goes to 1 at infinity. That is not allowed. But anything else, you can make it rise as slow as you want. That's okay. Okay? Right. So what are the kinds of guarantees? The thing that we like usually is that you look at the supremum of the loss, okay? And the supremum of the loss goes to 0. But then, this is not terribly interesting. Why is that? Because if the supremum of the loss goes to 0, it's a 0-1 loss function. It means from some point on, your loss was 0 forever, which means there is some CDF that is dominated by all the CDFs in the class. Okay? So why look at the data? You can just start off with this. Okay? So this just means that the class P is tight. There is a finite upper bound on every percentile. Just start off with this finite upper bound, because we don't care about how good the upper bound is. We just want a finite upper bound, right? So is this part clear?
By the way, this soup is random, right? You are not taking expectations.
There's no expectation, like because we have P, we have an estimate, right? So I haven't qualified exactly how this goes to 0 in this one, but okay, let's say we'll be looking at almost sure convergence. So yeah, so if for any, actually for any sequence you can manage this, it means there's a CDF that dominates. So why do all this, like just start off with that, right? So we look at something a little different, okay? So we just require that our estimate eventually upper bounds the CDFs of the underlying distribution. The convergence is almost surely, but there's no uniform convergence, okay? So this is a little more interesting because it need not happen that all the CDFs of the class dominate some universal CDF, okay? So somehow you need to learn something from the data, okay? And if you can do it, let's say you can even do this, okay? The question we are going to ask is something that qualifies this statement, and it's something every parent knows. So the question is, are we there yet, right? So eventually you know that you're going to do well, okay? So assuming that I even tell you that the unknown FP will dominate your estimate eventually, almost surely. The question is, with the data you have, how do you know how well you're doing? Okay, so that is sort of the crux of what we want to answer. Okay, so given just this data, can we say is a pointwise consistent estimate good or not? Okay, so essentially we have a series of results which we'll go over in the talk. So this is a lot of work that spans like the last 2.5 years. So for prediction and compression, we completely characterize when we can answer this question. When it is possible to answer the question, we'll show how. Okay. Which also means that there are cases where you cannot give an answer to this question. We'll see an example very shortly. Okay. Also, like what happens is, like when you require that, when you go away from just asking for pointwise consistent estimators, you demand that in addition to a pointwise consistent estimate, you also should be able to tell when you start doing well. It changes some things. Number one, everything depends now on how the property varies in the model class. Okay, so you look at any model in your model class, it doesn't matter how vast your entire class is. Okay, no global property matters. What matters is around the model, how does the property vary? So it's like there are a lot of rich people in the world, right? Bill Gates is very rich, but you just want to be richer than your neighbor, right? So it's that way. So you're just looking locally. You don't care about global properties anymore. Okay, so it changes the focus when you demand that you need to know from the data how well you're doing. Okay, it's also related to the question of robustness of priors, which a lot of Bayesians look at. We won't go over that. We won't have time for all that, but just as a aside. Okay, so at a high level, yeah.
Is there a random stopping here where you stop?
Right, so we'll formalize that. So yeah, there has to be like a universal stopping time. The stopping time obviously cannot depend on the unknown distribution. It should be universal for the entire class, and it should somehow indicate accurately that this is the point at which your accuracy is something. We'll come to that, yeah. So any other questions? Okay, so what we'll do is this, like we'll look at a simple example where you cannot answer this question, okay? So mainly because it sort of will make it clear like what is at play here. So this is an example that we call as hiding of entropy. Okay, why is it? Because we are looking at a class of distributions like this. You assign 1 minus epsilon to 0, and the remaining epsilon probability you distribute among m elements. Okay, now epsilon can be made as small as you want. Okay, epsilon can be 0 as well, but epsilon can also be made as small as you want. But when you make epsilon to be a very, very tiny non-zero quantity, you can still make capital M large enough that you can hide as much entropy as you want in the state. right? So our task is to estimate the entropy, and this tail will hit us, okay? So first thing is there are no uniformly consistent estimates. It's not hard to see. It's also easy to see that every distribution in this class has a finite support, okay? So if you just base your estimate of entropy on the empirical frequencies, okay, this one is almost surely going to be consistent, okay? The estimate of entropy purely from the empirical frequencies will be almost surely consistent because every distribution has a finite support, okay? The question we are going to ask is, so what we are going to observe, like it almost sounds like a poem, but it's something like this. There are some cases where you'll never be able to tell how good your estimate is, okay? So I started writing this, and yeah, so let R be any.
Is it 7 words every line?
No, I tried making it into something more interesting, but then I was too sleepy. So okay, so let R be any number, however large, eta be any confidence, however small. Like you look at a sequence, essentially it's like this. You look at a sequence of zeros, right? A long sequence of n zeros. You can never claim, no matter what your estimate of entropy is, you can never claim you're anywhere close to the true entropy. Why is that? Look at the sequence of zeros with right? So there is this distribution, right, which assigns probability 1 to 0 and 0 everywhere else. This gives this distribution, let's call this P naught, right? And then there are distributions where epsilon is really, really tiny, much, much, much smaller than 1 over n, right? But m is bigger than, let's say, 2 to the r over epsilon, okay? So what is the entropy of this source? It is bigger than epsilon log m, which is bigger than r, right? But this source, because epsilon can be made as small as you want, right? This also gives you can make it as close to 1 as you want by picking epsilon as small as you want, right? So because there is no bound on m, right, you can hide all the entropy in the tail, right? And because 1 minus epsilon is very, very close to 1, this sequence gets very high probability. So with so you cannot, no matter what your estimate is, right, it cannot be close to both 0 and r, right? So you can never get, and r can be completely arbitrary. Okay, so on this sequence of zeros, you will never be able to tell if you're doing well or not. Okay, even though you know that, like the plug-in estimate, which estimates 0 as the entropy, will eventually be consistent because, but then after any finite amount of time, there's nothing you can tell, right?
It's because you are taking the uniform over that class. And
Pardon?
take a soup over that class, then you cannot say anything. So essentially, the point was.
Oh, but there are a lot of classes, so that's what we'll see. This has nothing to do with just uniform. There are a lot of cases, even with pointwise consistent estimates, where you can still tell from the data what is happening. So it's a different thing from the, right. So it's not a question of just uniform and pointwise consistency. Like even in pointwise consistency, we'll see fairly complicated classes where there is no simple uniform consistent estimator, but you can still tell from the data how well you're doing. Okay, this is like how the Bayesians sometimes say that the data dominates the prior, something like that in that principle. Yeah.
So I don't fully understand the part of this example. The part of this example is what? This is a negative example.
Right. So this is a case where on this sequence of zeros, right, which happens with probability 1 under the singleton source, this source. Okay. Under this source with probability 1, you can never tell if you're doing well or not, no matter what your estimate is. Okay? So you have a case where where consistent estimation is possible, but you are never able to tell, at least for this source, you're never able to tell how well you're doing. Okay? So this is what we want to resolve. We want to ask when can you say how well you're doing and when cannot you say how well you're doing. Okay?
For every.
We want for every source. Right. So in a sense, this example is chosen because it is simple. It's kind of pathological because you remove this one source, everything works now. So this is a pathological example, but we also have many other cases, like most prominent being limp-elsive source codes, right? We know that for Markov sources of any memory, limp-elsive code length is asymptotically optimal. But if I give you like a 10,000 length sequence and ask you against the true source, not against a Markov source with memory k, I ask you against the true source, what is the redundancy? This means that you need to have some idea of what the order of the Markov source is. Okay? And that is a much harder problem. And in general, like, there isn't much you would be able to say. Right? So it's along the same principle. Here we are looking, of course, at IID data. We are not looking at something even as complicated as memory, because we just want to highlight this particular principle. Okay? Right.
This hypothesis seems like it says more source. Seems like the limiting point, or sort of all the other sources, right?
In this case, you're right. Like, so this source, we call it as a deceptive source because it sort of fools you into making an estimate while something else nearby hits you, right? So it's sort of cheating you. So, but then, like, in many classes, like including monotone distributions, for example, like every source behaves like this deceptive source. Okay, so So the point is like something like pointwise consistency. It has two flavors, where we can tell from the data how well we are doing and where we cannot, right? So what we ask is this: in addition to the estimate, which is pointwise consistent, we want a stopping rule. Okay, so this stopping rule sort of indicates when is it safe for you to say you're accurate. Okay, so this stopping rule. So there is one stopping rule for the entire class. Okay, so there's one stopping rule, so it is universal for the entire class. So the stopping rule has stopped means that your estimate has started doing well. Okay, so the bad thing is your stopping rule has stopped, but your estimate is still not accurate enough. Okay, that's the bad news. Okay, so for example, how would we phrase it for the prediction problem? Excuse me. So we want a stopping rule such that the rule has stopped, but you still are not doing well. This probability should be bounded with any confidence that I give you. Okay, so this is the bad event because your stopping rule somehow indicates that you're accurate, but in fact you're not. Okay, so this is the case where your stopping rule hasn't been able to tell you accurately whether or not you're doing well. Okay, so this bad event we want it to be as small as possible. Okay, so we call this, if you can do this, we call the class insurable. The reason is I'll give you a puzzle at the end and you'll see why we use that word insurable. Okay, you can do something very similar for compression as well. In compression, your loss doesn't converge almost surely to zero. Here it converges in L1 in mean, but it's like an unconventional rephrasing of the regular redundancy things, where where if this convergence is uniform, then it means it's strongly compressible with asymptotically zero per symbol redundancy. Where it's not, it's like Kiefer's weak universality. Okay, so we'll focus on just one though. So, right. So going back to the insurability, we'll just focus on this because I don't think we have time to ask for both. So going for this, it's actually very easy to say, like, what exactly must be satisfied for you to be able to tell from the data how well you're doing. Okay, so it's like a truthism, like around every model there's a simple neighborhood. Okay, that's what you need. That is both necessary and sufficient for you to be able to tell from the data how well you're doing. Okay, what does this mean? Well, like simple depends upon exactly the property you're estimating. We'll see what happens for the insurability case in just a little bit. Right. So, but some couple of points. The simple neighborhood around every model can be arbitrarily small. Okay, it doesn't have to be there need to be. It has to be non-zero. But as long as it is non-zero, the tiny simple neighborhood around any class can be as little as you want. It doesn't matter. Okay. Also, there's no requirement that the size of the simple neighborhood is sort of uniform around the across the class. Okay. So around every P, there's a simple neighborhood. Okay. And if you take the infimum of all these neighborhoods, it can be 0. Although, like for any single model, if I look at any single model, it must have a non-zero simple neighborhood. Okay. So the sizes of these neighborhoods can vary. Some neighborhoods can be very, very tiny. Some neighborhoods can be large. It doesn't matter. There's no lower bound necessary on the size of the neighborhood as long as it's non-zero. So essentially, what is happening here is like you're looking at a local property because you're not concerned about how, the class by itself can be very complex. What you are concerned about is around every model is a neighborhood simple. That's all you care about. Okay? Around every model is some neighborhood, however small, is it simple. Okay? So for the insurability case, so we have a characterization. Like you can tell from you can estimate these percentiles from the data if and only if some neighborhood around every model is tight. Okay? So in some tiny neighborhood around every model, you can do the problem trivially. Okay? So this is sort of the flavor, no matter what property you seem to consider. Like for compression, for example, you have something very similar. Like around every model, you need a small neighborhood that is strongly compressible. Okay? So your entire class need not be strongly compressible. The redundancy can be infinite. Nothing matters. Okay? Around every model is the neighborhood strongly compressible. That the neighborhood can be as small as you want. Okay? So that's the only thing that seems that would matter for data-driven characterizations. Okay? So how do we do this? Like it's a constructive proof, which I'm happy to talk about offline. But it's essentially like we exploit the fact that we are looking at countable alphabets, and so we have any class of models over naturals has a Lindelof property. So we managed to cover the entire class with a countable number of small good neighborhoods, and that's sort of the flavor of how we construct this scheme. Okay. So going back to what classes can you predict, for example? Okay. So the class of all distributions, all uniform distributions. Okay. Right. So the class of all uniform distributions, for example, that is insurable. This is not so strange because you look at samples from a uniform distribution, you can predict the value for the next sample as twice the maximum so far, and that's going to be more and more accurate as the number of samples goes to infinity, right? Exponentially fast. Okay, so this is not so strange. There is a more interesting class. Like we take uniform distribution, but we place a tail on them. Okay, this tail can be arbitrarily fat tails. Okay, it can diminish as low as 1 over n log n cubed. Okay. But even in these cases, so when you talk about being able to predict from the data how well you're doing, you're not implicitly restricting yourself to fast tails, or you don't need your distribution to have. You can still have your distribution having heavy tails. Okay, so again, like it means like you don't care about like whether the tails are fat or not. If a distribution has a fat tail, you just care about whether the surrounding distributions are similar or not. Okay, so essentially, like we can actually predict even when you have very, very fat tails. They have arbitrarily long uniform distributions followed by a very, very slow diminishing tails. Okay. And it's actually pretty interesting to compare how these properties hold. And this is the last slide. So how the properties hold when you look at compression and insurability. So this is strongly compressible classes which we are currently focusing on. The sizes of the boxes are a property of Xfig. It's not an indication of how large classes are. Okay? So, but what gets us, so we are going away from this little green box, and insurable classes are a much broader classes, and there are interestingly classes where you can predict, but you can never compress. There are classes where you can compress, but you can never predict. There is everything in between as well, right? So I can go over all of this offline if anyone is interested. I'll be here for this week, next week, and again from April 15th till the end of the program. So thank you.
Thank you. Maybe you get lucky.
So, yeah. Lucky. Yeah. Lucky is a matter of perspective because, like Max said, it means you have to get up early.
Or you can sleep late. Right.
Yeah,
So
that is true.
Question?
Any questions?
You have a question there?
Oh.
Explore the connection between your setting and your perspective with, high quantile influence in extreme value theory?
No. So I'm not actually familiar with this one, but to the extent I've seen people do similar things in compression. Like particularly, they have this notion of hierarchical compression where you nest classes of models, and you want redundancy to be actually comparable to the particular class the source belongs to. But then the question we are asking there is sort of complementary because we don't care if the redundancy is just correct. We want to know what the redundancy is. So the identity of the class label is what we are asking about. But we can talk about this. I'll be very interested in knowing this. So, yeah.
Okay. Since we're rolling into the discussion, so maybe we can leave the questions to discussion also.
Sure. Yeah.
Okay. So we can roll into the discussion. So two things. We're going to vote for our lucky talk again tomorrow. So since Alon already used this trick about tricking students to help out last time, so I can't use the same trick again. So what do? Hey, Alon. So who's going to help me out?
Who is below 30?
Handing out the discussion. And let's get a bunch of chairs. So
Yeah.
2 chairs. Set up the front.